Hello, everyone. So it's almost like a cleansing experience to present in front of your peers that co-create and share the same dreams with you. In that sense, I approach the opportunity that the organizers gave me as a way for me to clarify what we have achieved over these 2.5 years. We're a relatively new group that was formed at Rutgers University in 2015, and what deserves, if not demands, a future. To conceptualize this talk, I will give a brief overview of these 15 years of brain research that I've conducted and I'm bringing to brain-morphic computing. There are two main components of this work. The first component is robotics, robots that imitate a brain function, the work that I did at McGill University, or attempt to restore brain dysfunction, and I'm referring to the MIT pediatric ankle-bot that I developed, and this work overcame the gravitational force of the lab setting, and it's being used on a daily basis in 3 hospitals. The second component that I'm bringing to brain-morphic computing is the usual suspect, computational neuroscience, essentially data-driven spiking neural networks that help us understand a little bit something more about the brain pathophysiology or inform possible treatments such as deep brain stimulation, or help us understand or create methods for early intervention in the case of autism, a work that I did at Harvard Medical School. So in 2015, I joined Rutgers and I formed the Computational Brain Lab with a single goal, which is to understand biological intelligence and translate that understanding to artificial intelligence by developing brain-morphic computational methods that integrate with the brain across the spatial and the temporal scales. So the two principal components of what we do is we understand brain function and we abstract away computational principles and apply them to what we call generic data analysis. In fact, this goal is not new and it's not ours. 1950s, von Neumann, and even before him, the usual suspect, Alan Turing, made quite interesting analogies between what was then the current state of knowledge of how the brain works and computational principles. Now, both von Neumann and Turing based their theories on the McCulloch-Pitts neuron as a basic processing unit in the brain that was developed in the 40s. So if someone looks at all these 60, 70 years, he or she will find many analogies like that. Take, for example, reinforcement learning. It was developed based on the behavioral studies that were again done in the 50s about how pigeons or their brain can identify, prioritize, and anticipate rewards in an effort to keep a balance between exploration of an uncharted territory and exploitation of an unknown knowledge. Going one step further, 2013, convolutional neural nets, the workhorse of today's deep learning, became very successful because they use a single principle from the brain, that of receptive fields, which was again introduced back in the 50s. To address the main disadvantage that CNNs have, their feature spatial invariance, Hinton quite recently introduced or reintroduced his idea of capsule neural nets that, again, are using a single principle from the brain, that of the cortical microcolumns that was formed, again, back in the 50s. So the main argument I want to make is that if we are to realize our promise that we will develop brain-morphic computing methods, we should fill this gap here. Of course, this sampling is not dense, is not complete, but it gives a trend that we also need to follow. And I don't need to convince anyone, at least in this room, that over these 30 years, we did not only experience a huge amount of new knowledge of how the brain works, but we also have now modalities that allows us to see brain function in different ways that we never had the chance to use before. For over 100 years, this neuronal paradigm of studying the brain has been prevailing brain research and has been at the forefront of emerging disciplines such as computational neuroscience and artificial intelligence. So take, for example, medicine. If I develop a brain disease, I will be assessed by a neurologist, and if needed, I will be treated by a neurosurgeon. And this conception, this dogma that brain equals neurons is not only prevailing in traditionally conservative fields such as medicine, but artificial intelligence is based on this conception that brain equals neurons. And there are good reasons for that. There are actually two good reasons for that. Since neurons are electrically active cells, for over 100 years, we know how to stick electrodes close to them and record their electrical activity. And within that activity, we know that neurons encode, process, and output information. The other reason that makes neurons so prevalent is that we can manipulate them, again, because they're electrically active cells. So it comes as a surprise to many to learn that up to 90% of the brain cells are not neurons. These brain cells, which are called glia cells, have been remaining silent for these 100 years. And to give an idea of this conception or misconception that all these cells were doing was nothing, you can take their name. Glial cells comes from the Greek word for glue. So the perceived view for many years was all these neurons, all these cells are doing is that they provide nutritional and structural support to neurons. They're the glue between neurons. Not until recently, where in the last 15 years we've seen, again, an explosion in a new way of seeing how the brain works in calcium imaging, which allows us to see how calcium goes up or down, is used as a signal inside the cell of, inside the brain cells. Astrocytes, which are the most dominant brain cell, about 40% of our brain cells are astrocytes. We knew about them. So this is Ramon y Cajal's drawing back in 1897, where he looked at these brain cells through the lens of his microscope, and he drew them. So we knew about the existence of these cells. What we could not see was their function. Until very recently, where you can see that these cells are using calcium, that's one way, that they use calcium to receive information from their periphery, process it, and then send again that information back to their periphery. Now, these astrocytes are not just cells that hang around neurons as neurons are doing their thing. In fact, astrocytes form their own communication network within the brain. And there's something more than that. The astrocytic component of our brain and the neuronal component of our brain interact with each other through synapses. That's why we call them tripartite synapses. In fact, the whole brain node comprises of astrocytes and neurons talking to each other and interacting with each other as they process information. So in the last few years, we've been seeing yet another paradigm shift in neuroscience, where astrocytes are now starting to be considered as a key cell when it comes to processing information. And there are two main opportunities for someone working on a field that one could name computational astroscience. One opportunity is to create computational models and help understand how behavior and diseases emerge out of that interaction between neurons and astrocytes. The second opportunity is to create neural astrocytic networks that will give us two major advantages. The first advantage is that they will expand learning beyond the weight changing. The astrocyte is the third part of a synapse, and it takes its own role in learning. The other thing that is important if astrocytes are considered is time, that now goes beyond the discrete instances. Interestingly enough, astrocytes have their own dynamics, and their time scale is very similar, if not identical, to the behavioral timescales that we experience. This is where the good news stops. How do you model this? Well, the neuronal paradigm of studying the brain has given us enough ammunition. This is a slide that I so like that I actually stole from Dr. Mayer's talk. So there are two major ways to do it. To approach the physical phenomenon, either a neural spiking activity or a calcium astrocytic activity, as an emergent phenomenon by looking at the biophysics, or as a black box, as a target function. So how do you build a neural astrocytic network? The first component that you need, since you need that time-sensitive computational formalism, is a spiking neural network. The second component is the astrocytic layer. One way, there are multiple ways that you can model the astrocytic waves. One way that I want to present here is that global calcium wave that is called spontaneous. And every 30 seconds or so, people observe these waves that propagates across the spatial and temporal domains of the astrocytic tile. So we can model that by looking at the amplitude and the shape. And you can see here a less aesthetically pleasant but more scientifically accurate representation of how these waves propagate in space and time. And these red circles are astrocytes that control the neurons. Now, that's the interesting thing here. How astrocytes control neurons. This is happening in the so-called tripartite synapse. And I told you that up to 60% of our synapses are actually tripartite synapses. And what the astrocyte does is actually three things. The first thing that it does is it listens, it hears what the neuronal component is saying. The other two things that it does can be captured to a single word. It modulates the neuronal component. How? By inhibiting the presynaptic neuron and or injecting current into the postsynaptic neuron. Therefore, it introduces its own information with its own dynamics into the neuronal brain. There are multiple ways. Well, there are a few ways to model this. One way that we followed is the so-called gatekeeper model, which is essentially a modification of the TAM model. And it allows us to also look at that phenomenological variable F, which looks at the ability of the astrocyte to inhibit the presynaptic neuron. And the other part is the ability of the astrocyte to actually inject current into the postsynaptic neuron. And these equations have been fit to experimental data. In other words, when an astrocyte calcium gets elevated high enough and reaches a threshold from below, the astrocyte injects current into the postsynaptic neuron. So we have everything. We have the information that is going through the synaptic cleft from one presynaptic neuron to the next postsynaptic neuron. And we have the ability of the astrocyte to modulate the activity by that F and the I-seq, the current that it injects. We created a neural astrocytic network in a very similar way by just looking at the, or modulating the, well, modeling the connectome, a typical connectome that you would expect in a cortical layer. And we put it to sleep. So that network did not do anything. It didn't have a function. We just have a neuronal component that was driven with a basal activity. And on top of it, we had that astrocytic wave modulating the neuronal component. Interestingly enough, when we put that network to sleep, oscillations that can be found when people and rats sleep emerge. Delta oscillations emerge out of that interconnection between neurons and astrocytes. It's a pure computational study. However, 2 months after we archived our paper, we got an experimental validation of our results through a paper that I'm showing here. So we started scratching our heads saying, if by not doing anything, that neural astrocytic network is threatening to scratch the surface of a 100-year-old question. Oscillations in the brain are one of the most well-studied component of biological intelligence, but less well understood. We don't know the mechanistic origin. So we said, if this is happening with a network not doing anything, what would happen if we introduce a function to a neural astrocytic network? So what we did is we, again, kept it as simple as possible. We started with a Hopfield network for two main reasons. The first reason is that the Hopfield network is a precursor of deep belief networks and restricted Boltzmann machines that are heavily used. But it's also simple enough to help us mathematically analyze and study. And the second reason for looking at Hopfield nets is that the interesting things in the Hopfield net are actually happening in the synapses where neurons and astrocytes interact. So for those of you who are not aware of what a Hopfield net is, it's a fully connected recursive network of binary state units that creates, well, whenever we create a memory, we essentially create a valley in the energy field that is associated with the global state of the network. So the neurons, by looking at their neighbors, they change their state or not. And the overall global function it relaxes into one of these attractors, which are essentially the memory states of the network. So our goal was to find a learning rule for astrocytes that would generate a transition between memories. This is just a disclaimer. Whatever you see as green is our own astrocytic contribution to the black Hopfield, original Hopfield mathematical formulae. I'm not going to go into the details of the math. I'm going to intuitively present them. So what we did is we introduced an astrocytic component to that neuronal local field. And essentially what the astrocytes did is that they introduced the time, and that time is actually coming from the dynamics of the calcium as it increases over as the result of a presynaptic neuron activity. And when it reaches a threshold, the astrocyte is injecting current into the neuronal component. So this time here is the most important thing because it takes us from the fast processing of the neurons to the much slower time that we expect to see in a behavior. In fact, we derive time by keeping things biologically plausible or as biologically plausible as possible. And what we ended up having, and I'm just going to present the plot. It's much better than the math. What this plot says that if the astrocyte is confident enough about what it hears in the neuronal component, it's fast in injecting current. If it needs its own time to assess what is really happening at the neuronal component, so the time that it injects the current, which is related to the time that it takes for the calcium to increase, also increases. So overall, this is the result. We see that the network changes the states from mu1 to mu2, mu3, and so on and so forth. And that change of the memories was due to the astrocytic contribution. In fact, although it's not mathematically accurate, you can think of that as the network relaxes to one of these attractors, and as soon as it relaxes, the astrocytic component starts to tilt that energy field until it reaches the second memory, and so on and so forth. This is one way to train astrocytes, and it's a Hebbian type. It's the simplest thing that we could think, and this is one that I want to present here. So essentially what we do, we have that learning rate, and the most important thing is that time. So we need to wait enough for the astrocyte to sense through the elevation of the calcium, and then what we do is we have an association, like autocorrelation between, cross-correlation between the two memory states So essentially, what the astrocyte learns is the amount of the injected current that needs to be added to the postsynaptic neuron to cause that change from one memory to the other. So overall, what did we discover? We introduced at least one example where learning is expanded beyond that weight change. We have the third member of the connections of the synapses, which is the astrocyte, that can have its own learning and its own dynamics in that learning. I want to thank this talk would never be possible if I didn't work with two brilliant undergraduate then students, Kevin and Leo. It's not a coincidence that both of them are now PhD students at Stanford and MIT. Leo stayed with us for more than a year and a half to 2 years, so we corrupted him even more. And I want to present something like as a preview of perhaps next year's contribution to NIS. We're taking both directions. We're looking at the ability of the astrocyte to sense the neuronal component, and we also take the AI perspective, trying to do generic data analysis tools where neural astrocytic networks are actually working together. This is a video that I got from Giannis, one of my PhD students, 2 days before the start of the conference, and it shows how astrocytes can sense and impose synchronicity in small areas of neurons. So this is the first talk that I will give. The second talk will be about that bottom part, the robotic component, the robotic framework that we built to host these neural astrocytic networks. And the talk will be a lighting talk tomorrow. And I would like to thank you and take any questions that you might have now or in the break. Thank you.
Thank you. Thank you very much. Are there comments? Yes. Could you go to the microphone, please? Go to the microphone, please, so that we can.
I once was an ardent believer in a particular role to be assigned to astrocytes as control units, as Charles Anderson called for them. And then what put me off it was an experimental paper out of a group in San Diego that proved that astrocytes are territorial. The volume filled by an astrocyte is not penetrated by another astrocyte. And I found that so unnatural to this kind of network operation that I turned away from that idea. What do you say to that?
I wouldn't say that whether you did right or wrong. Time only will assess about this. All I'm saying is that the experimental data suggests that astrocytes do communicate with each other through gap junctions. So they send calcium waves from one cell to the other, and this actually creates a territory. In fact, nobody knows what is the functional reason for the astrocytes creating tiles in the brain. And one of the interesting things is that their geometry is something that nobody has actually used in terms of their computational role. It's hard for me at this point, at this stage, to comment and make like a strong argument either for or against what you said.
Other comments? Questions? If not, then let's thank the speaker again.